So in 11.1, we learned about sequences, where we have a string of numbers that form a pattern. And in 11.2, we learn about when you add the sequence, it becomes a series. Now they say that the sum of an infinite sequence becomes a series. So again, we have these terms. So this is an infinite series here, and we just call it a series. And it's written as the summation, and I'm sure you've seen that before. That's the capital letter sigma. So the summation of a sub n, or the summation of a sub n from n equals 1 to infinity. So that's our notation for a summation. And sometimes you wonder, is it reasonable to talk about the sum of a bunch of terms? So with that in mind, think about this problem. If I'm adding these, this is our set of whole numbers. So if we're adding these, you can't really add all of those. We need to put a plus in here. So when you add those, it just gets larger. So the sum here is divergent, and it doesn't make any sense to try to add them. If we add the first two terms, we have 3. If we add the first 3 terms, we have 6. So we can take what we call a partial sum. If we had the first 4 terms, we have 10. But we can't add them all up. If we look instead at 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... plus 1/2 to the n, you can see that these are getting smaller and smaller. So let's look at some partial sums. If we add the first term, we get 1/2, which is 0.5. If we add the first 2 terms, we have 2/4 plus 1/4 is 3/4, which is 0.75. If we add the first 3 terms, we have 1/8 plus 1/4 plus 1/2. So this becomes 7/8, which is 0.875. Now, this you don't really have to write down. We do it. So this is the sum of n terms. The first 4 terms, we get 15/16, and I don't know that decimal approximation. Probably 0.84, and so forth. So if we look at the sum, this one's in the book, so this shows the sum. Now note that about here, we could say that the sum, about on the first 7 terms, we could say that the sum is approaching 1, but look, it gets closer and closer and closer to 1. So we can use what we call partial sums to help us estimate what the sum is approaching. The partial sum can help us determine the specifics about an infinite sum. So we say that the sum of the first term is A1, S sub 2 is A1 plus A2, S sub 3 is A1 plus A2 plus A3. So these are partial sums here. S sub 4, is A1 plus A2 plus A3 plus A4. So they'll help us determine whether or not we have a limit here. But S sub n equals A1 plus A2 plus A3 plus ... plus AN. So this equals the sum of the A sub I terms, where I begins at 1 and ends at n. So then this will help us figure out what's happening in the general or infinite series. And we can say if the limit as n approaches infinity of S sub n equals some sum, if this exists, then we can find the sum of the sequence A sub n. So we have a definition. So in this definition, if we're given a series, we let S sub n denote its nth partial sum, just like we talked about earlier. And if the limit, the sum converges to a number, like the previous example, it converged to 1, then the series is called convergent, and we can write it like this. If this number S, the number S is called the sum of the series. So if the sequence is divergent, then we call the series divergent. So you have to pay attention to the sequence, and then that will help you determine what's happening with the series. So up here, see, if the sequence is convergent, then we'll be able to find a sum. And if the sequence is divergent, then the series is divergent. So the sum of the series is the limit of the sequence of partial sums. So when we say the sum from n equals 1 to infinity of a sub 1 equals s, that's this notation right here. We say that if we add enough series, we can get close to the sum of the sequence. So if we have this summation notation, we can look at it as the limit, and look at the limit as n approaches infinity of the summation from I equals 1 to n of a sub I. So let's use that. Consider S sub n equals a sub 1 plus a sub 2 plus a sub n. So this sum is 2n over 3n plus 5. Now notice the sum equals that, not a sub n equals that. So using the statement up here, we're going to play with this a little bit right now. And we say the sum from n equals 1 to infinity of an. So we're going to use the fact in the box up here and say that the limit, this is equal to the limit as n approaches infinity of the sum S sub n. Now we know that, let's keep the limit, let's go down. So the limit as n approaches infinity, and we know that S sub n is equal to 2n over 3n plus 5. So if we plug in infinity, we have infinity over infinity, indeterminate form. So let's use the technique where we divide by the highest power of n in the denominator. So n over infinity. So we divide, we have 2n divided by n is 2. 3n divided by n is 3. And here we have 5 over n. So we know this approaches 0, so we have 2 over 3. So the sum of the series is 2 over 3. Now, you're not always given this formula for the sum, but remember the geometric series that we looked at in 11.1, that it's one of the 3 main types of series and sequences. So it looks like this. You have I usually call it A1, AR squared, AR to the third, AR to the fourth, and so forth. AR to the n minus 1. So this equals the sum from n equals 1 to infinity of AR to the n minus 1, where a does not equal 0. So this is a geometric series. Sorry, we started with the sequence. This is a geometric series, and R is your common ratio. So that says I'm multiplying by the same value every time. Let me give you an example. If I have 1/2 plus 1/4 plus 1/8 plus 1/16. This means my first term is 1/2, and my common ratio is 1/2. So if I multiply by 1/2, I get 1/4, and if I multiply by 1/2 again, we get 1/8. So you can see that's happening. It doesn't always have to be a fraction. You could have 3, and then have 12, 48, 192. So that in this case, your first term is 3, and your common ratio is 4. Now this one is divergent. You can see that because the sequence is divergent, the series, let me turn them into pluses, the series would also be divergent. So let's go back and talk about a geometric series for a minute. So here we find that a geometric series is convergent if my common ratio is less than 1. We kind of saw that with the two examples that we looked at. And then we have a formula for its sum. So the sum is right here. If the absolute value of r is less than 1. If the absolute value of r is greater than 1, then the series is divergent. So we generally say the sum of a geometric series is a over 1 minus r. A is your first term. A is equal to a sub 1, and r is the common ratio. And then, so we have the first term divided by 1 minus the common ratio. Now this is true if the absolute value of r is less than 1. I tend to say if it's a fraction, it's a little easier to remember that way. But that indicates that your terms are getting smaller, and you can find the sum of the geometric series. If your absolute value of r is greater than or equal to 1, if it's a whole number, your terms are getting larger and the series is divergent. So if you're interested in that, we've talked about bits and pieces of this. We've talked about up to about here, and we've talked about some of the rest. But if you'd like to read the proof of where it comes from or how it works mathematically, it's right here. So feel free to pause the video. Now, when you read a math book, you need to get out pencil and paper and do the steps that they're skipping. So they listed out the terms of the series, and then they multiplied everything by r to go up one more series. And then they subtracted the two terms. So if you subtract them, then you end up with this equation, and factor and divide. So it's not a difficult equation to see where this comes from, and you can continue to work through it. So this next problem says find the sum of the geometric series. All right, so when we look at this, we know that our first term is 5. Now, if this is geometric, our life is a lot easier. So we're looking for the sum of this series. So we're going to look at the common ratio, hopefully. So if I take my second term, 10/3, and divide it by 5, that's the same as negative 10/3 times 1/5. So that gives me negative 2/3. So if I multiply negative 10/3 by negative 2/3, I do get 20 over 9. And if I multiply that by negative 2/3, I do get negative 40 over 27. So we do have a geometric series. And so a geometric series is great. Because I know that the sum is equal to a over 1 minus r. So a is 5, and I have 1 minus negative 2/3. So I have 5 divided by 1 plus 2/3. So I have 5 over, let's see, that would be 5/3. So this means I have 5 divided by 5/3. So we have 5 times 3/5, which is 3. So the sum of the geometric series is 3. So what does it really mean that the sum is 3? That means if I add up all of these terms, I get closer and closer and closer to 3. So consider this. So if we were to add up a bunch of sums, you could see that it kind of bounces around. This graph to the right here, this is not the sequence values, this is the sums. Notice this is S sub n. So the sum kind of bounces back and forth around 3. And you can see down here we're getting closer to 3. But the more we add, the closer we get to 3. That's why it's considered a infinite sum, and we can get close to 3 because we have a geometric series and we know that it happens. Look at this sum. It says the sum from n equals 1 to infinity, 2 to the 2n, 3 to the 1 minus n. There's two ways to look at this. We can look at it algebraically, or we can list out the first few terms. Let's do the first few terms. So a sub 1 would be 2 squared, which is 4, times 3 to the 1 minus 1, which is 0, so it's just 1, so we have 4. And a sub 2, so I have 2 times 2 is 4, so I have 2 to the 4th times 3 to the negative 1, so we have 16 over 3. A sub 3, we have 2 to the 6th and 3 to the minus 2. So 2 to the 6th is 64 over 9. And a sub 4 is 2 to the 8th and 3 to the minus 3. That's 256 over 27. Can you see a pattern here? We would continue, but we know that A is 4, and if you pay attention, the common ratio is 4 over 3. So that's one way to do it. The other way to do it is to say, okay, let's do some algebra here. We have 2 to the n, 3 to the 1 minus n. Now, if I can make this look like a r to the n minus 1, it's geometric. So the other option is to look at the algebra here. So we have n equals 1 to infinity. So this is 2 squared to the n power. And this is 3. Well, I would like an n, not a 1 minus n. So let's factor out a negative. And this becomes negative 1 plus n. So come down again. We have 1 to infinity, the sum. 2 squared, by the way, is 4 to the n. And we have 3 to the negative n minus 1. Let's just switch them. So let's move that term with a negative exponent to the bottom of the fraction. That's a good thing because we need a fraction for our r in order to work with a geometric series that converges or that has a sum. So on the top we have 4 to the n, and on the bottom we have 3 to the n minus 1. Now we need their powers to match. We need them to both be n minus 1 because that's our definition of r. So we're going to say n equals 1 to infinity. And here let's take 4 times 4 to the n minus 1. Because if you put an understood 1 here and you add them together, it becomes 4 to the n. So you can do that over 3 to the n minus 1. So now we can say the sum from n equals 1 to infinity. And I have a 4, and I'm going to have 4 thirds to the n minus 1 power. So here you can see that a equals 4. That's my first term. Because if I put 1 in there, then the power on the fraction becomes 0. And r is 4 thirds. Also, if you go back up here, it follows this pattern. That's your pattern for a geometric series. So whether you work with it by looking at the first few terms, or if you manipulate it to come up with this, then we say the sum is equal to a over 1 minus r. But notice that's when the absolute value of r is less than 1. We have a fraction, so we tend to want to throw it in there and run with it. But 4 thirds is greater than 1, so that means that this series is divergent. So you don't use this formula when r is greater than 1. This formula happens when r is less than 1. When r is greater than 1, when the absolute value of r is greater than 1, then we have divergent. So this series is divergent. A drug is administered to a patient at the same time every day. Suppose the concentration of the drug CN measured in milligrams per milliliters after the injection on the end of the day. Before the injection the next day, only 30% of the drug remains in the bloodstream, and the daily dose raises the concentration by 0.2 milligrams per milliliter. So when you walk in, the person has 30% of the concentration of the drug from the day before. That's 0.3 CN. And now you're adding 0.2 to it. This is just, we're going to add 0.2 milligrams per milliliter to it. So we say C sub n plus 1 equals 0.3 CN plus 0.2. So that's where we build this formula from. So we know that C sub n plus 1 equals 0.3 CN plus 0.2. Now, the problem says find the concentration after 3 days. So the concentration after 1 day is 0.3 C sub 0 plus 0.2. Well, on the day before, you didn't put any in, so that is 0.2. We could make a note up here that C sub 0 equals 0 because there was no drug in there. And then C sub 2 is 0.3 C sub 1 plus 0.2. So I have 0.3 times 0.2 plus 0.2. So that's 0.06 plus 0.2 is 0.26. And then C3 equals 0.3 times C2 plus 0.2, which is 0.3 times 0.26 plus 0.2. So this equals 0.278. That's one of these recursive sequences that are a series that we talked about the other day. So the concentration after 3 days for part A is 0.278. That's equal to C3. So that's part A. We could have done part A differently to help us with part B. So I'm going to do that again. And I'm going to rearrange it just a little bit. So I'm going to call this part A again. C1 equals 0.2 plus 0.3 CO, and we know that that's 0, so it's 0.2. And then C2 is 0.2 plus 0.3 C1. So this would be 0.2 plus, now we're going to leave the 0.3 in it, so let's say 0.2 times 0.3. And I know I switched them, but that's called the commutative property, and it's allowed. Now we know this equals 0.26, but we're looking for the pattern on this one. So let's say C3 is 0.2 plus 0.3 times C2. So we have 0.2 plus 0.3 times, and C2 is 0.2 plus 0.2 times 0.3. So if we distribute that, we're going to have 0.2 plus 0.2 times 0.3 plus 0.2 times 0.3 quantity squared. Let's go ahead and look at C4 just to help solidify this pattern for us. So this is 0.2 plus 0.3 times C3. So we're going to have 0.2 plus 0.3 times C3 is 0.2 plus 0.2 times 0.3 plus 0.2 times 0.3 quantity squared. So if we distribute this, we get 0.2 plus 0.2 times 0.3, this first term in the bracket, plus 0.2 times 0.3 squared, plus 0.2 times 0.3 to the third. So we can build a pattern now, dot, dot, dot. So C sub n equals 0.2. Now notice that here I have just 0.2, 0.3 to the first, 0.3 to the second, 0.3 to the third, and this happens to be n minus 1. It doesn't happen to be, it is. So we're going to say 0.2 plus 0.2 times 0.3 plus 0.2 times 0.3 squared plus dot 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 plus 0.2 times 0.3 to the n minus 1. So that builds the pattern for the nth term. So you can see we can find an exact term up here, but if we can build it out and say that this really equals 0.2 and this equals 0.26, and we look at the patterns while we go, then we can build a pattern for the nth term. So this is part B, the pattern for the sum for our nth dose. But we know here that A is 0.2 and R is 0.3. So we can find a finite sum. But we have a formula. We have a formula for partial sum of a geometric sequence, and it says S equals A times 1 minus R to the n over 1 minus R. This is our formula for a partial sum. So if we use that here, we could say that C sub n equals A, which is 0.2, times 1 minus 0.3 to the n over 1 minus R, and R is 0.3. Sorry about that. So this equals 0.2. Let's do it this way. 0.2 over 0.7, 1 minus 0.3 to the n. Now 0.2 over 0.7, that is 2/7. 1 minus 0.3 to the n. And that's a better formula for our concentration after the nth dose. What we have up here, this one helps us recognize the pattern to see that it is geometric. So we can use the summation formula and summarize it to be such. So then in part C it says, what is the limiting concentration? What is the limiting concentration? So let's take the limit as n approaches infinity of Cn. So we have the limit as n approaches infinity of 2/7 times 1 minus 0.3 to the n. So that would be the limit as n approaches infinity. I don't know why I'm rewriting it. Sorry, 2/7, 1 minus 0.3 to the n. 0.3 is a decimal, and it gets smaller and smaller. So as we put in infinity, 3 to the infinity approaches 0. So we end up with 2/7 times 1, which is 2/7. So the 2/7 milligrams per milliliters is the limiting concentration. So I think we'll stop this video here and pick up with the next one. Thank you.